Hello, this is Dr. Hanaa Assil, and this is the second part of our review on paper 6, which is the experimental techniques needed for IGCSE Chemistry. So, if we talk about acids, bases, and salts, you should know that an acid is a proton donor, a base is a proton acceptor, and the word proton here refers to the H plus ion. So the acid gives H plus ions, the base accepts H plus ions. You should be familiar with the pHs for different solutions. A strong acid like hydrochloric acid or sulfuric acid would have pHs 1, 2, and 3. A weak acid like vinegar or ethanoic acid or lemon juice would have pH 4, 5, or 6. A neutral solution or water or salts will have pH 7. A weak base like ammonia will have pH 8 or 9 or 10. You give him one of them. And a strong base like sodium hydroxide, calcium hydroxide would have pHs 11 or 12 or 15 or 14. And you should know indicator is a substance that has different colors in acids and bases. So if I want to know if a solution is an acid or a base, we just put in litmus paper. In acids, it turns red. In base, it turns blue. But if we want to know the pH of a solution, then I tell him insert universal indicator paper and compare the color to the chart. Remember that the colors of the universal indicator paper for strong acid and strong base, they're just like litmus. Strong acid is red, litmus is blue. A neutral solution, the universal indicator would be green. For a weak acid, it is orange or yellow, and these are the colors that you should be familiar with. Phenolphthalein or methyl orange are solutions that we use in titration. You should know the colors. Phenolphthalein in a base is pink. In neutral or acid, it would be colorless. Methyl orange is yellow in base. In neutral, it is orange, and in acid, it is red. The method that we use to prepare a salt depends on what we're using or what we're preparing. So you should know which salts are soluble and which salts are not soluble. You should realize that any nitrates are soluble, sodium salts, potassium, anything, ammonium, anything is soluble. All acids are soluble. Things like barium chloride, copper sulfate are all soluble. Of course, if we say they're soluble, that means their state symbol is aqueous, and the word aqueous means dissolved in water. Now, things that are insoluble, most carbonates are insoluble. So you should know that barium carbonate is insoluble, calcium carbonate is insoluble, silver halides, lead halides, so silver chloride, bromide iodide, lead chloride, bromide iodide, things like barium sulfate, copper oxide, all metals, all of these are insoluble, and that means their state symbol would be a solid, S for solid. Now, which method are we going to use to prepare a salt? Well, if we're trying to prepare a soluble salt from soluble reactants, everything is soluble, then we use the method called titration. So, for example, I'm trying to prepare sodium chloride crystals. How do we prepare sodium chloride crystals? First of all, you should know that sodium chloride will be prepared from sodium hydroxide and hydrochloric acid. And then I need to know how much I should add in order to have a neutral solution. I don't want excess acid and I don't want excess base. So we do the method called titration, and in titration we have burette and flask. We put 25 centimeter cubed of the base, usually the base, sometimes it could be the acid in the flask, but usually we put 25 centimeter cubed of the base in the flask using a pipette. Then we add 3 drops of indicator. This could either be phenolphthalein or methyl orange. If it is phenolphthalein, then the solution initially will turn pink. Add dilute acid from the burette. Of course, what we do is we fill the burette We notice the initial volume in the burette, and then we add drop by drop until the pink color turns colorless. Note the amount of acid used. So now I know how much acid I should use with 25 centimeter cubed of sodium hydroxide. Now, if he's telling me to prepare the salt, then I have to repeat using the required amount of acid to the same amount of base without indicator. Remember that that initial flask has indicator in it. Now, heat the solution to point of crystallization, cool, filter the crystals, wash with a few drops of distilled water, and dry between filter papers. And this is how we prepare a pure dry sample of sodium chloride. So remember, if he says state one safety precaution that should be taken when using dilute sulfuric acid, remember that we said acids are corrosive, so we need to wear gloves. Now, in a titration, we usually do this titration using a white tile. Now, if he says, why am I using the white tile? This is to see the color change clearly. Describe what should be done to the apparatus labeled A as the dilute sulfuric acid is added. Remember, as I add the acid, I should be swirling the flask in order to mix the contents so that we can get the correct volume of acid needed. Usually, he says, when we're doing titration, I have to wash the burette first with water and then with the acid that I'm going to fill it with. So why am I washing it with water? To remove traces of any previous solutions. And then why am I going to wash it with the solution that I'm using? This is to remove the water. I don't want any water in the burette, or it would affect the concentration of the acid that I am using. Then sometimes we use the burette for something else, not titration. If I have two solutions, I have solution A and solution B, and I want to know which of these solutions is more concentrated. Now, if these solutions are bases, then I can titrate them with acids. So I fill the burette with acid. Do it once with solution A, do it once with solution B. The solution that is more concentrated will use more of the acid. So remember, if I am using different solutions in the flask, then the one that takes more of the acid in the burette is the more concentrated. But what if it is the other way around? My flask has a certain amount of a certain solution of dilute sodium hydroxide. Once I'm going to titrate it with acid A in a burette, the other time I'm going to titrate it with acid B in the burette. Now, in this case, the amount of acid, the one that I use more of it, is the less concentrated. So if I needed more of A than B, that means A is less concentrated. Okay, this is a typical experiment. Oven cleaners contain aqueous solution of sodium hydroxide. Plan an investigation to show which of the two different oven cleaners contains the more concentrated solution of sodium hydroxide. So I'm going to use titration to compare two solutions of sodium hydroxide, and I want to know which one is more concentrated. So I'm going to tell him, put 25 centimeter cubed of the first sodium hydroxide solution into a flask using a pipette. Add 3 drops of phenolphthalein. The solution turns pink. Of course, I could also use methyl orange. In that case, the solution would turn yellow. And then add dilute HCl from the burette until the pink color disappears of the phenolphthalein. Note the volume of acid used. Now repeat using the same amount of the other alkali. The one that uses what? The one that uses more acid is the one that is more concentrated. The other method of preparing a salt is called neutralization method. In neutralization method, I am starting with something that is insoluble. For example, I want to prepare copper sulfate. Now, copper sulfate would be prepared from sulfuric acid. I cannot say copper plus sulfuric acid because copper alone will not react with sulfuric acid. I need to use copper oxide, which is a base. Now, this method is different. I'm not doing titration. What I'm going to do is I'm going to add solid copper oxide using a spatula to 25 centimeter cubed of sulfuric acid in a beaker. And remember, this does not have to be exact. So I'm not going to use a pipette. I could just use a measuring cylinder for the acid. And if he says why, it is because I'm using excess of the other reactant anyway. I'm using excess copper oxide, so I don't need the sulfuric acid exact. Now, if he says, why am I using the excess solid? I will tell him to make sure that the acid has reacted, to make sure that all the acid has reacted. Then I filter. I don't want this excess solid, so the excess solid will be collected as a residue. That's not what I want. What I want would be the filtrate, because that is the solution of copper sulfate. Then I heat the filtrate to point of crystallization, cool, filter the crystal. The other method of preparing salts is called precipitation. In precipitation, I'm trying to prepare something that is insoluble. So for example, I'm trying to prepare silver chloride. Silver chloride is a solid. It does not dissolve. In order to prepare it, I have to add two solutions. So I need two soluble reactants. So silver something. We said all nitrates are soluble. So I will start with silver nitrate. Something chloride. We said all sodium salts are soluble. So I can use sodium chloride. Now, when I add the two solutions, what I get is the precipitate. So what I'm doing is add silver nitrate solution to sodium chloride. Remember, they have to be solutions. So if he says they are originally solids, I have to tell him that I'm going to dissolve it in water to make solutions and then add them together. Silver chloride forms a white precipitate. Then I filter. In this case, I want the residue. I want the precipitate itself. So filter through filter paper and funnel, wash the residue with a few drops of distilled water, and dry between filter papers. Please remember all of these. Then the next thing you need to know is the tests, the qualitative analysis, the tests for the different anions or cations. So for example, we have a test for carbonate ions. Do you remember that? We said for carbonate ion, add dilute acid. So specify any acid. It can be dilute hydrochloric acid, or if he says he added dilute sulfuric acid, if he has a carbonate, he should get bubbles of gas that turn lime water milky, because carbonates with acid give carbon dioxide gas. Test for halides. Halides are chloride, bromide, iodide. For all of them, I add dilute nitric acid and silver nitrate solution. Remember, dilute nitric acid and silver nitrate solution. If I have chloride, it's a white precipitate. Bromide, cream precipitate. Iodide, yellow precipitate. Remember, these are tests for the halide. So this is test for chloride, not for chlorine. There's another test for chlorine. This is for chloride, bromide, iodide. Test for nitrate. What was the test for nitrate? Well, add aqueous sodium hydroxide, then aluminium foil, warm gently. Nitrates should give ammonia gas, so I will get bubbles of gas that turn damp red litmus paper to blue. Are we following? Test for sulfates. What was the test for sulfates? Add dilute nitric acid and then barium nitrate or barium chloride with hydrochloric acid. If I have sulfate, I should get white precipitate. What if I don't have sulfate? If he says I have something chloride, for example, and he added barium nitrate, then no effect. The barium nitrate will give white precipitate only if I have sulfate. Test for sulfite ions. Sulfite, what do? We add dilute hydrochloric acid, warm gently. We get bubbles of gas that turn acidified potassium manganate from purple to colorless. Remember that if it is sulfite, I add acid and warm, it gives which gas? It gives sulfur dioxide gas. Now, what is the test for sulfur dioxide gas? I pass it through acidified aqueous potassium manganate. That means potassium manganate with acid, like sulfuric acid. And the permanganate originally is purple, it will turn to colorless. Test for aluminium ions. These are cations now. Aluminium ions, I can either add sodium hydroxide or aqueous ammonia. If I add aqueous sodium hydroxide to something that has aluminium, what should I get? White precipitate, soluble in excess, giving colorless solution. Are we following? What if I add aqueous ammonia? And remember that aqueous ammonia is ammonia solution, is ammonium hydroxide. Now, if I add aqueous ammonia to something that has aluminium, what should I get? White precipitate, insoluble in excess. That means if I continue to add the aqueous ammonia, the precipitate remains. Okay, test for ammonium ions. What do? We add aqueous sodium hydroxide. Now, on warming, what should I get? Bubbles of gas that turn damp red litmus paper to blue. Now, if he asks me what is the name of the gas, then it is ammonia gas. But remember, observation is just bubbles of gas that turn damp red litmus paper to blue. And remember, when we're using litmus paper to test gases, it has to be damp. Test for calcium. What was the test for calcium? If I add aqueous sodium hydroxide, I should get a white precipitate insoluble in excess. With aqueous ammonia, no precipitate or very slight white precipitate. Test for chromium ions. We said if I add sodium hydroxide, I get green precipitate, soluble in excess, giving a green solution. With aqueous ammonia, I get a gray-green precipitate, insoluble in excess. Have we memorized all of this? Please memorize all the tests. Test for copper 2. Copper 2, if I add aqueous sodium hydroxide, I get light blue precipitate, insoluble in excess. That means as I add more and more sodium hydroxide, the precipitate remains. But if I add aqueous ammonia, at first I will get light blue precipitate. But if I continue to add the aqueous ammonia, the precipitate dissolves, so it is soluble in excess, giving a dark blue solution. Test for iron 2. Whether I add sodium hydroxide or aqueous ammonia, in both cases I will get green precipitate, insoluble in excess. For iron 3, whether I add sodium hydroxide or aqueous ammonia, in both cases I get reddish brown precipitate, insoluble in excess. This is iron 3. Test for zinc. In both, whether aqueous sodium hydroxide or aqueous ammonia, I get white precipitate, soluble in excess, giving a colorless solution. Please remember all of these tests. Then the test for gases. Remember we said ammonia, insert damp red litmus paper, it turns blue. Carbon dioxide, bubble the gas through lime water. The lime water turns milky. Remember that lime water is calcium hydroxide. If you pass carbon dioxide through it, it becomes milky because it forms calcium carbonate, which is a white precipitate. Chlorine gas. Remember, there is test for chlorine, and the other one was test for chloride. Chlorine, insert damp blue litmus paper, it bleaches. We said bleaches means it turns white. Hydrogen, insert a lighted splint, it pops. Oxygen, insert a glowing splint, it relights. Please memorize all of these. Now, flame tests. How do we do a flame test? If he says explain how to do a flame test, we said clean a platinum wire by dipping it in concentrated HCl. Then dip the wire in the salt, expose the wire to the non-luminous flame of the Bunsen burner, the part of the Bunsen burner flame that does not have a color, and observe the emitted light. Remember the colors. We said lithium will give red, sodium yellow, potassium lilac, copper is blue-green. Please remember all of these. The other tests in organic, we said we have a test for alkenes. The test for alkene was add bromine water. It turns from reddish brown to colorless, or we call it orange to color. Test for ethanol or organic flammable liquid. Put a lighted splint near the liquid, it catches fire. So if he says he put the lighted splint near a liquid, it catches fire, that means that I have an organic flammable liquid, or specifically ethanol. Ethanoic acid, remember we said ethanoic acid, that's the chemical name for vinegar. So the appearance is a colorless liquid, the smell is smell of vinegar. And these colors are the colors that you're supposed to know. So for example, group 7, we said fluorine is a yellow gas, chlorine is a green gas, bromine is a reddish brown liquid, iodine is a gray solid. And then we said copper. Copper as a metal, remember most of the metals are silvery in color, except copper. Copper is reddish brown. Now, the compounds of copper, copper sulfate, copper hydroxide, these are blue. Copper carbonate, you should know, is green, and copper oxide is a black solid. Remember magnesium, if I burn magnesium, it gives magnesium oxide, and this is a white ash. Nitrogen dioxide gas, when we talk about metals, they will give nitrogen dioxide gas. When the nitrates are heated, this is a reddish brown fume. Carbon is a black solid. So if he says that he heated an organic compound and it gave a black solid, then that black solid is probably carbon. Manganese dioxide is used as a catalyst for decomposition of hydrogen peroxide. It is also a black solid. Then we talked about rates of reactions, and you should be able to explain the rates of reactions and draw graphs for rates of reactions. So remember, when we increase the temperature, the rate increases. Why is that? Particles gain more kinetic energy, move faster, collide faster, more of the molecules have energy higher than activation energy, so there will be more effective collisions. So you increase the temperature, they have more energy, they collide faster. Remember, when we draw the graphs, if he has a graph for a slower reaction, then it is the one below. A faster reaction, then it is the one on top if he's using the same amount of reactants. Another thing we can change is the pressure. Remember, pressure applies only for gases. So if the equation has gases, I can tell him increase the pressure. Increasing the pressure would increase the rate. And we said this is because the particles would be closer to each other, so more collisions per minute. Surface area, we said if we use lumps, big pieces, or if we use powder. Now, which one is faster? We said the powder is faster, or the smaller pieces is faster. So crushing a solid or using smaller pieces increases the rate. Why? Because the one that is powdered has larger surface area, so more particles collide at the same time or more frequent collisions. Concentration. If I use a more concentrated solution, then the rate is faster. Again, why is that? Because then I will have more particles in the same volume, so they will more collisions at the same time. Catalyst, remember, a catalyst increases the rate of reaction without being changed. Now, why is that? You have to be able to explain that this provides an alternative pathway that lowers the activation energy. So whether I'm talking about an exothermic or an endothermic reaction, the reaction with a catalyst will have lower activation energy. Remember, we said activation energy is the distance from the reactants to the top. So the uncatalyzed has higher activation energy, the catalyzed has lower activation energy. Enzymes, remember, are biological catalysts, so they are catalysts inside living cells. Studying rates of reactions, we said if the reaction gives out a gas, then I can measure the volume of gas per minute using a gas syringe. And we said for any reaction, at the beginning, the reaction is fast. Why? Because I have more particles colliding. But at the end, the rate slows down and becomes zero. Now, why? Because the reactants are being used up. Usually you will have to look at the beginning of the experiment and find out which one is excess and which one is not excess. So if he says, why did the reaction finish? I will tell him because the one that is not excess has been used up. Again, these graphs, when you draw them, so if you're drawing for an experiment that we're going to call A, now you should realize that experiment 2 is faster, experiment 1 is slower. Now, when do we get experiment 3? If I'm using more reactants. So in A and 1 and 2, I'm using the same amount of reactants, so I get the same final volume of gas. But in experiment 3, I used, for example, twice the amount of magnesium, for example, then I will end up with twice the total volume of gas. Another method of measuring the rate of a reaction is putting the flask on a balance. In this case, we're measuring the loss in mass, and this is possible only if this reaction is giving out a gas. So I put a cotton wool at the mouth of the flask. If he says, why do I have a cotton wool at the mouth of the flask? It is to allow the gas to escape but prevent loss of solution by splashing. Of course, I can then draw a graph of the mass versus time. The mass at the beginning will decrease, and then once all the reactant has been used up, then it will become constant. Remember that in this graph, the experiment 2 is a faster reaction than experiment 1. Now, if the reaction is not giving out a gas, if it is forming a precipitate, then I have to use another method in which I put an X on a paper, put my flask on the X, and I take the time, I measure the time taken for the X to disappear. So in this case, the reaction is not giving out a gas, it is forming a precipitate. You should realize that if I have sodium thiosulfate, that is Na2S2O3, this is called sodium thiosulfate. When it reacts with acid, one of the products is sulfur solid, which is a yellow precipitate. So I measure the time taken for the X to disappear, for the cloudiness to be so much that I cannot see the X. And of course, I can make a graph of time versus temperature. For example, if I'm doing this experiment several times at different temperatures, remember, a faster reaction takes less time. Okay, this question says an aqueous solution of hydrogen peroxide decomposes very slowly to form oxygen. The speed of decomposition can be increased by using a catalyst. Two possible catalysts are copper oxide and chromium oxide. Plan an investigation to find out which of these is the better catalyst. So what do? We use this kind of setup and we tell him what? We want to know which one is better. So I'm going to use a certain mass of the first catalyst, weigh 5 grams, for example, using a balance, put into a flask connected to a gas syringe, add a specific amount of hydrogen peroxide to the flask, for example, using dropping funnel, and then determine the volume of gas collected in a certain amount of time, collected in 2 minutes, for example. Then I'm going to repeat using the same mass of the other catalyst, the same amount of hydrogen peroxide. The one that gives more gas in 2 minutes is the better catalyst. Sometimes he tells you to compare the energy value of fuels. So he says I have ethanol and methanol, for example. I want to know which one is a better fuel. So what I do is I measure 25 centimeter cubed of water into a test tube using a measuring cylinder. Determine the initial temperature of the water using a thermometer. Then I weigh a specific amount of the first fuel, 25 grams, using a balance. Place the burner below the test tube and light it. Allow it to heat the water for a specific amount of time, 5 minutes. Note the final temperature of water, and then I'm going to repeat it using the same amount of the other fuel and the same volume of water for the same amount of time. determine the final temperature of the water. And then how do I know which one is a better fuel? The one that causes a higher increase in temperature of the water is the better. Sources of error in this experiment, of course, in any experiment in which I'm heating something, one source of error would be loss of heat to the surroundings, or if I am burning the fuel, it could be incomplete combustion, so it is not giving out as much heat as it should. If he says any precautions I should take, well, I can tell him insulate the experiment to prevent loss of heat to the environment. Or instead of using a glass test tube, I should use a copper can because, of course, the copper is a better conductor of heat. This is a typical question. Unsaturated fats and oils contain at least one carbon-to-carbon double bond. These double bonds react with bromine water, which changes color from orange to colorless. Plan an experiment that could be carried out to compare samples of different oils to find out which of these contains the largest number of carbon-to-carbon double bonds. So, what should I do? He says you're provided with common laboratory apparatus and organic solvent to dissolve the fats and the oils. Well, what should I do then? I put a certain amount of the first oil in a test tube. Remember, he's giving me an organic solvent, so I need to dissolve it, for example, in ethanol. So I say add 10 centimeter cubed of ethanol using a measuring cylinder to dissolve it. And then what am I going to do? I can add drops of bromine water using a dropper and count the number of drops needed for the orange color to remain. Remember that as you add the bromine water at the beginning, it will react with the double bond and it will become colorless. Again, it will become colorless until I have used up all the double bonds in the fat. Then any drop of bromine water, the orange color will remain. So here I'm counting the number of drops needed for the orange color to remain. Repeat using the same amount of the other oils. The one that needs more drops has more carbon double bond carbon. Electrolysis. Remember, electrolysis is the breakdown of an ionic compound by the passage of electricity. So we have this kind of setup where the electrode is a rod that allows electric current to pass through. Remember that if we need an inert electrode, it is either made of graphite or platinum. And the electrolyte is the solution or molten compound that conducts electricity, so it has to be ionic with positive and negative ions that are free to move, so it has to be molten or an aqueous solution. Remember that when we have this kind of setup, what is happening? The electrons are flowing in the wire, the positive and negative ions are moving in the electrolyte. Remember, electrons are negatively charged, so in the wire, the electron is moving towards the positive end of the battery and away from the negative end of the battery. Remember that the cathode is the negative electrode that is connected to the negative end of the battery, so the metals or hydrogen will go to the cathode. The anode is the positive electrode that is connected to the positive end of the battery, so the negative ions, which are non-metals, are formed at the anode. So for example, if I have electrolysis of molten sodium chloride, for example, and we're using inert electrodes, remember, if I have sodium chloride, the chlorine will form at the positive, the sodium will form at the negative. Chlorine is a green gas, so if he says what is observed, it is bubbles of green gas, while at the cathode, it is a gray metal that deposits. If I have molten lead bromide, again, molten means I heated it until it melted. Now, it is the bromine that will form at the anode, so I will see reddish brown fumes. Remember that the product at the anode is bromine, not bromide. Now, at the cathode, the product is lead, and that means a gray metal deposit. If I'm doing, for example, electrolysis of molten copper to chloride, then what do I have? I will have chlorine, bubbles of green gas at the anode, and the copper at the cathode. Copper is a reddish brown metal. These were molten. Now, if I have aqueous solution, what we have now is the ions from the compound I'm doing electrolysis of, plus the ions of water, which are H plus and OH minus. So if I have, for example, concentrated HCl, now I have a choice for the positive. I have either chloride or hydroxide to react. Remember that we said if we have a choice between chloride and hydroxide, the one present in higher amounts is the one that reacts. So concentrated HCl has more chloride, so it is chlorine that forms at the positive. And at the negative, the cathode, of course, I don't have any other positive ion except the H plus, so I form hydrogen gas at the cathode. Now, if I have concentrated sodium chloride, again, at the anode, I have a choice between chloride and hydroxide. It is the chlorine that will be formed. On the cathode, I have a choice between Na plus and H plus. Remember, if I have a choice between Na plus and H plus, the hydrogen is the one that reacts. Remember, the one that is less reactive in the reactivity series is the one that reacts in electrolysis. So hydrogen is the one that forms, and I'm left with sodium hydroxide solution. And that means that if this solution has in litmus solution or indicators, then the indicator will become blue because sodium hydroxide is formed. If I'm doing dilute sodium chloride, now which one is present in higher amounts, chloride or hydroxide? Now it is hydroxide. So the hydroxide, when it reacts, it gives oxygen. So with a dilute chloride solution, it is the hydroxide that reacts to form oxygen. At the cathode, I still have a choice between Na plus and H plus. It is the H plus that will form hydrogen gas. In aqueous copper sulfate, if I'm using graphite electrodes, then what happens is I have a choice between sulfate and hydroxide. Remember, sulfate never reacts. So it is the hydroxide that will react to give oxygen gas. On the other end, I have a choice between the copper ions and the H plus ions. Now you should know that copper is less reactive than hydrogen, so it is the copper that will form, and in solution I will be left with H plus and SO4 2 minus, so I'm left with sulfuric acid. So my blue solution of copper sulfate will become colorless because it has changed from copper sulfate to sulfuric acid. If I'm doing electrolysis of dilute sulfuric acid, these are the ions I have. I have a choice between sulfate and hydroxide. Which one reacts? The hydroxide is the one that reacts to give oxygen. On the other end, I will have hydrogen gas. Now, electroplating is covering a metal with another metal using electrolysis. So if I have a spoon and I want to cover it with silver, now I put a silver rod at the positive. So the silver rod is the anode and my spoon is the cathode. What happens is the silver dissolves from the anode, so the silver electrode becomes smaller. The silver ions go to the cathode and cover the spoon, so I get a gray silver metal dissolving, depositing on the object. How do we do that? This is how we explain it. Connect the silver rod to the positive end of the battery using copper wires. Clean the surface of the spoon with sandpaper. If he says, why do I have to do that? It is to allow the silver to stick to the surface. So the first thing I need to know is I should clean the object with sandpaper. This is to allow the silver to stick to the surface. Then I put the spoon in a beaker containing silver nitrate solution. Remember that the solution has to be a solution of the metal I'm trying to cover it with. So if I'm trying to cover it with silver, it will be a solution of silver nitrate. If I'm trying to cover it with something else like nickel or chromium, then my solution should be nickel nitrate or chromium nitrate. Connect the spoon to the negative end of the battery, and that will cause electroplating of the spoon with silver. Of course, if I want to electroplate it with another metal like chromium, then my anode will be a chromium rod. Reactions of metals with oxygen. Remember that all metals react with oxygen to form oxide. And the oxides of metals are usually basic. You should know that sometimes they're amphoteric, but they're usually basic. And something like magnesium, for example, if I burn it in oxygen, you should realize that magnesium burns with a bright flame or a white flame, and the magnesium oxide that is formed is a white solid. This is an experiment. He's saying calcium burns in air to form calcium oxide. The reaction is vigorous and some of the calcium oxide can be lost as smoke. Plan an investigation to determine the maximum mass of oxygen that combines with calcium. So I'm trying to burn calcium in air and he's telling me how much oxygen is it using. How am I going to know how much oxygen it is going to use? Well, I'm going to burn it, weigh it at the beginning, burn it and weigh it at the end, and the difference between that will be the amount of oxygen. So what we do is we put a specific mass of calcium into a crucible and lead, weigh using balance, cover the crucible and heat it, remove the cover several times. Why are we removing the cover several times? Because I need to make sure that I have enough oxygen entering into the crucible. Why don't I cover it completely? Because I want some oxygen to go in. Why don't I leave it without a cover? Because if I leave it without a cover, then I could lose some of my calcium oxide that is being formed. Then I weigh the crucible and lid. How do I know if the reaction has finished? I have to heat and weigh and reheat and reweigh until the mass remains constant. So we say reheat and reweigh till constant mass. Now, if we subtract the initial mass from the final mass, this will give me the amount of oxygen that was used by the calcium. Reaction of sodium with cold water. You should know that sodium, potassium, sodium, calcium, they react with cold water, and when they react with cold water, they give the hydroxide plus hydrogen. Now, what do I see? Group 1 have low density, so the sodium floats, darts, melts. I have vigorous fizzing due to evolution of hydrogen gas, and the bubbles of hydrogen gas may catch fire. It is forming sodium hydroxide. So if I test the solution with litmus paper, it turns blue. Now, if I'm doing the reaction with calcium, I put calcium in cold water, it will still give me the hydroxide plus hydrogen gas, but now the calcium sinks. I still have strong fizzing, but the solution becomes milky because the calcium hydroxide that is formed is not soluble in water. Please remember all of this. You're supposed to remember. When magnesium reacts with steam, now starting from magnesium, zinc, iron, and so on, these will react with steam. When they react with steam, they give the oxide plus hydrogen. So when I react magnesium with steam, the magnesium burns with a bright flame. The magnesium oxide that is formed is a white solid, and I have a hydrogen gas coming out. The same with zinc, it will give zinc oxide plus hydrogen. If I'm reacting with acids, remember the reactivity series. Any metal above hydrogen would react with acid. So magnesium, for example, would react with acid. Zinc would react with acid, but copper is below hydrogen. Copper does not react with acid. Remember, if he has comparisons between the different metals, the one that gives more bubbles is the one that is more reactive. Displacement reactions, if I have a more reactive metal, it will push the less reactive metal from its salt. So zinc is more reactive than copper. It will react to displace it. So you should know that copper sulfate, for example, is blue Now, when it reacts, what are the observations that I see? The blue color of the solution becomes colorless. The zinc solid that I added at the beginning will dissolve. It is forming copper, so it is forming a red precipitate that will be formed in the solution. Magnesium plus copper carbonate. Again, magnesium is more reactive than copper, so it will displace it and give copper back. Plan an investigation to show the order of reactivity of 3 metals. So he gives me 3 metals and I want to know which one is more reactive. Again, I'm going to weigh a certain mass of the first metal using balance. Put into a conical flask connected to a gas syringe. Add a certain amount of HCl to the flask using a dropping funnel. Determine the volume of gas collected in a certain amount of time. Now repeat using the same mass of the other metals, the same volume of HCl. The one that gives more gas in the same amount of time is more reactive. Please pay attention to all of this. Again, here he's saying brass is a mixture of 2 metals, copper and zinc. Copper does not react with acid, zinc reacts. Plan an investigation to find percentage by mass of zinc. So what should I do? I weigh at the beginning. Weigh 10 grams of brass using balance. Put into a beaker. Add excess acid and heat. Stir with a glass rod until no more solid dissolves. Filter through filter paper and funnel. The copper, which is the one that did not react, will be collected as residue. Wash the residue with a few drops of distilled water. Dry between filter papers. Weigh the residue. He wants percent of zinc, so I subtract the mass of the copper from the initial mass to get the mass of zinc. Calculate the percent zinc, and that would be your answer. Rusting. Remember that rusting needs water and oxygen. So he says you're provided with iron nails and 3 different samples of water. Plan an investigation to find out which sample of water causes iron to rust. So I have tap water, distilled water, and seawater. And in this case, how do I know which one has rusted more? I weigh the iron nails at the beginning, put into the test tubes, add equal amounts of the water, leave at the same temperature, so tell him leave at room temperature for the same amount of time. Of course, rusting is slow, so we leave it for 5 days. After that, remove the nails, put into separate beakers, dry in an oven, weigh. The one with more increase in mass is the one that has rusted more. Sometimes he has this experiment in which he has iron wool at the top in the measuring cylinder. And if we leave it for 2 weeks, for example, we find that the water in the measuring cylinder goes up. Now, why does the water go up? Remember that the iron uses up oxygen from the air for rusting, and the water goes up to replace the oxygen that was used in rusting. Now, after 4 weeks, the water is still the same. This is because all the oxygen has been used up, so no more rusting. This is another experiment. Solutions of chemicals known as corrosion inhibitors are added to the water in steel radiators to reduce rust. You are provided with 3 different bottles of liquid corrosion inhibitors. Remember, the word inhibitor means something that prevents corrosion. And some steel nails. Plan an experiment to test if these inhibitors prevent corrosion of steel and which of these is the most effective. So this is the opposite of the other one. We want to know which one will not cause rusting. So in this case, I'm going to do the same thing, but I want to know which one is a better inhibitor. So weigh each nail using a balance, put into different test tubes, put the same amount of water and 10% and 20 centimeter cubed of water and 10 centimeter cubed of one of the inhibitors into each test tube. Leave at room temperature for 5 days, so same temperature, same time. Remove the nails, place into separate beakers, dry in an oven, weigh. Here now I have to tell him the one with less increase in mass is, the better inhibit. In extraction of metals, remember we extract metals from their ore. The ore is the raw form of the metal obtained from the earth. The method will depend on how reactive my metal is. Any metal that is more reactive than carbon, I have to get it by electrolysis because it is more reactive than carbon and will not be displaced by it. But metals that are less reactive than carbon can be extracted by reduction by coke, since the metal is less reactive than carbon and it can be displaced by it. So you should remember, how do we extract aluminium? We extract it from its ore. The ore of aluminium is bauxite. The method is electrolysis. Now, we need molten. Remember, in order to get the metal, I need molten, not solution, or I will get hydrogen instead of the metal. So molten aluminium oxide melts at a very high temperature. I have to add cryolite. Why am I adding cryolite? To lower the melting point of aluminium oxide. The electrodes are made of what? They're made of graphite, which is actually carbon. So what happens? At the cathode, I get aluminium. The aluminium ions gain electrons and become aluminium. Now at the anode, I get oxygen because the O2 minus ions of the oxide lose electrons and become oxygen. But then this is causing oxygen gas to come out at an electrode that is made of carbon. So the electrode burns. The anode burns in oxygen to form carbon dioxide gas. So the anode has to be replaced from time to time. Extraction of iron, we said iron is less reactive than carbon, so I don't need to do it by electrolysis. I can do it by reduction with coke. The ore of iron is hematite. Hematite is Fe2O3. This reactions happen in a huge sort of building which we call the blast furnace. At the top of the blast furnace, we put coke, limestone, and the ore, which is the hematite. And at the bottom of the blast furnace, we put hot air. That means my four raw materials are coke, limestone, hematite, and air. Now, the first reaction that happens is the coke burns in oxygen to give carbon dioxide. This is a very exothermic reaction and helps to raise the temperature of the furnace. But then I still have a lot of coke, so the carbon dioxide is reduced by coke to form carbon monoxide. And the carbon monoxide is the reducing agent that will reduce my hematite, Fe2O3, to form iron. The iron will go down as molten iron to the bottom of the blast furnace. Now, we also added limestone. You should know that limestone is calcium carbonate. The limestone breaks down in the heat of the furnace to form calcium oxide, and the carbon dioxide gas escapes. Now, the calcium oxide will react with the main impurity in the blast furnace, which is sand, which is silicon dioxide. The calcium oxide is a base. It reacts with the silicon dioxide, which is acidic, to form calcium silicate. The slag floats on top of the iron. So when it floats on top of the iron, it prevents the reoxidation of the iron. And then when we remove it from the blast furnace, it is used in road making. Then this molten iron that we get from the blast furnace, we still need to purify it. We bubble hot oxygen through it. This oxidizes the carbon to carbon dioxide gas, sulfur to sulfur dioxide gas, and the gases escape. Now the rest of the impurities form acidic impurities. I add calcium oxide, which is a base, to neutralize the acidic impurities. It forms slag that floats on top of the iron and is removed. I can then take the iron and add the required amount of carbon or other metals in order to form the different types of steel. We can extract copper from its carbonate by, first of all, heating the copper carbonate. It will change into copper oxide, and then I pass hydrogen gas over the copper oxide, and that changes it into copper Of course, you should remember that the copper carbonate originally was green. When I heated it to become copper oxide, it becomes black. And the copper oxide, when it is reduced by hydrogen to form copper, the copper is a reddish brown solid. I can also extract it by a different method. So if I have something called malachite. Malachite is a mixture of copper carbonate with other things. I want to make copper from it. So the first thing is I crush the malachite in a mortar and pestle. I put it into a beaker and add sulfuric acid. So in this case, I am changing the copper carbonate into sulfuric acid, into copper sulfate. So the copper carbonate changes into copper sulfate. I filter this to remove the impurities, and then the copper sulfate solution, if I add magnesium to it, remember that magnesium is more reactive than copper, so it will displace the copper. If I filter, I get the copper as a residue. You should remember uses of water at home: drinking, cooking, washing. In industry, we use it for cooling, making beer, making soft drinks. In the paper industry, in hydroelectric power stations, these are the uses of water in industry. Here, this is an experiment. He says the mineral epsomite contains hydrated magnesium sulfate. When epsomite is heated strongly, it loses water, eventually becomes anhydrous magnesium sulfate. Plan an investigation to find the percent by mass of water in this sample. Of course, what we do is we weigh a certain amount in a crucible and lid using balance, heat using Bunsen burner, allow to cool, weigh the crucible and lid, and we said, as before, we said we keep reheating and reweighing until constant mass. Subtract the final mass from the initial mass to calculate the mass of water, and the percentage would be the mass of water over the initial times 100. Then we have chemical test for water. You should remember that we add anhydrous copper sulfate. It turns from white to blue. The physical test would be heat to boiling. It should boil at 100. How do we purify water? We go through two steps: filtration to remove suspended solids, and chlorination to kill harmful bacteria. We could have an experiment to determine the percentage of oxygen in air. So he has air in two syringes. He's passing the air over heated copper, so the copper will react with the oxygen, and then he determines how much the decrease in the volume of air, the decrease in the volume of air would be the volume of oxygen that was present. How do we prepare oxygen? Remember, we prepare oxygen from hydrogen peroxide solution using manganese dioxide as a catalyst. Oxygen is not soluble in water, so it can be collected over water. This experiment says sulfur dioxide gas is a common pollutant formed when fossil fuels burn in air. Sulfur dioxide can be detected by using an acidic solution of potassium dichromate. The dichromate solution changes color from orange to green when a certain amount of sulfur dioxide has reacted with it. Plan an experiment to investigate which of three different samples of coal produce the most sulfur dioxide. So in this case, I'm going to have a setup like this. I weigh 10 grams of the first sample of coal, put into an evaporating dish, cover with an inverted funnel connected to a delivery tube, and the delivery tube is going into a specific amount of potassium dichromate. Put the delivery tube into the test tube, burn the coal, measure the time taken for the orange color to change to green. And then I repeat with 10 grams of the other samples of coal using the same volume of potassium dichromate. The one that causes the faster changing color has more sulfur dioxide. Carbon dioxide, how do we prepare carbon dioxide? From marble chips. You should remember that marble is calcium carbonate with acid. How do we collect carbon dioxide? You should remember that carbon dioxide gas is heavy, so we collect it by downward delivery. We use carbon dioxide to make soft drinks because it forms acidic solutions, so it gives it that sour taste. And we use it in fire extinguishers because it is heavier than air. Ammonia, you should remember that ammonia gas is less dense than air and very soluble in water. Ammonia is a base, so it reacts with acid to form salts. It forms the ammonium salt. It is less dense than air, so we collect it by upward delivery. This experiment says fertilizers are used to increase the growth of plants. Fertilizers have to dissolve in water if they are to be used by plan an experiment to find the solubility in grams per 100 centimeter cubed of a certain fertilizer at 30 degrees Celsius. So what do? Weigh 100 grams of the fertilizer, for example, using balance. Put into a beaker, add 100 centimeter cubed of water using measuring cylinder because he wants the solubility in 100 centimeter cube. Heat to 30 degrees Celsius, this is the temperature he wants. Stir the solution until no more solid dissolves. Filter through filter paper and funnel. Dry the residue between filter papers. Weigh, subtract from the original mass to determine the mass of fertilizer that dissolved in 100 centimeter cubed of water. Here, another experiment. He says, I have two different fertilizers. A farmer decides to buy one of these fertilizers to improve the soil on his land. Plan an investigation to find out which of these fertilizers would be best to grow beans. He wants to grow beans. So, obtain two bean seedlings with the same same height, same age, same species. Measure the initial height of each seedling. Put the seedling into the same amount of soil. Add equal amounts of water. Weigh equal amounts of fertilizers using balance. Add one to each soil. Leave for 5 days at room temperature, so it is the same time, same temperature. Measure the final height of each seedling. The one with more increase in height is the better fertilizer. I hope it was useful to you. Thank you for listening and good luck on the exam.